In episode 4, we derived a complete solution for the spectral composition of the quantum vacuum, when polarized by the presence of matter. This polarization effect transforms the quantum vacuum into the polarizable vacuum model of general relativity. In this episode, we utilize the complete solution articulated in episode 4, to predict variations in the Casimir effect, associated with various gravitational environments. Let's begin with a quick review of the complete solution formulated in episode 4. Appearing on screen is the complete solution, as formulated in episode 4, defining the spectral composition of the quantum vacuum. As indicated, the complete solution includes the harmonic cutoff frequency, harmonic cutoff function, harmonic cutoff mode, fundamental vacuum frequency, quantum vacuum amplitude spectrum, quantum vacuum frequency spectrum and refractive index of the polarizable vacuum, that is, the refractive index of space-time. Please pause the video and study the information provided. We encourage our viewers to review episodes 1 to 4 before proceeding. Let's now take a quick look at the cubic frequency distribution underpinning the nature of the quantum vacuum. Our cubic frequency distribution demonstrates that spectral energy density increases with gravitational intensity. In this illustration, we have broken the cubic frequency distribution into 4 regions. Region A relates to cosmology, whereby space-time geometry has been experimentally confirmed to be flat. Region B relates to the astrophysical scale of cubic frequency distribution, whereby space-time geometry has been experimentally confirmed by general relativity to be curved. Region C relates to the particle physics scale of cubic frequency distribution, whereby space-time geometry is usefully approximated as being flat. Lastly, in Region D, at the theoretical Planck scale of cubic frequency distribution, space-time geometry is assumed by the scientific community to be curved. The dominant gravitational model associated with each region refers to the state of the quantum vacuum. In Region A, the quantum vacuum exists at its minimum energy condition. The name given to the quantum vacuum in this condition is zero-point field. In regions B, C and D, the quantum vacuum is polarized by the presence of matter and the quantum vacuum is termed polarizable vacuum. With respect to the extraterrestrial Casimir effect, we shall be executing our calculations within region B. Let's now take a quick look at the harmonic mode distribution underpinning the nature of the quantum vacuum. If we now look at the harmonic mode distribution, we see that it increases as spectral energy density decreases. Region E, representing the Planck scale, indicates that with sufficiently large mass, the number of harmonic modes equals unity. The important takeaway from this illustration is that the number of possible harmonic modes in the quantum vacuum tends to infinity as the quantum vacuum approaches its zero-point field ground state. Conversely, as gravitational intensity, that is, space-time curvature, increases, the quantum vacuum harmonic mode population decreases. With respect to the extraterrestrial Casimir effect, we shall be executing our calculations within region G. Thus far, we have executed a high-level summary of quantum vacuum spectral characteristics as derived across episodes 1 to 4. If viewers are familiar with these episodes, then you should have found this to be somewhat nostalgic. For viewers unfamiliar with episodes 1 to 4, then the summary presented, up to now, should act as a skeleton going forward. Next, we will be adding flesh to the bones by revisiting a presentation we made in 2011. So, let's dive into it. In 2011, we presented a research article at a conference in San Diego. The article was titled, The Extraterrestrial Casimir Effect. In this article, we contribute to the discourse regarding the nature of light, via the Casimir effect. So, let's begin. What are we going to cover? We have quite a bit to get through, but we're going to cover 10 key areas. These are, number 1, the Casimir force. What is it and how is it generated? Number 2, the zero-point field. What is it and how does it manifest? Number 3, the polarizable vacuum. What is it and how does it relate to the zero-point field? Number 4, the polarizable vacuum model of gravity. What is it, how is it different to general relativity, and what can it do for us? Number 5, electrogravimagnetics. What is it and how can it be used? Number 6. The zero-point field frequency distribution. What is it and what major problem does it cause in physics? Number 7. The zero-point field cannot contain infinite energy in flat spacetime. This relates to the infinite energy in the vanishing volume problem. Number 8. Zero-point field frequency bandwidths. If the space-time manifold can contain infinite energy in the vanishing volume, the associated zero-point field must be frequency limited within a bandwidth. What is it? Number 9. The extraterrestrial Casimir effect. If a Casimir experiment was conducted in an extraterrestrial environment, will a different force be measured? Number 10. Extraterrestrial predictions. If the Casimir force varies, depending upon the local gravitational environment, what will it be in specific situations? The central theme running through this presentation is that the Casimir force as historically derived, represents an average cosmological quantity because of the manner in which it was formulated, but we will discuss this in the coming slides. So, what is the Casimir force? The Casimir force is literally a force from nothing. It arises when two parallel, neutrally charged, reflective, metallic surfaces are in close proximity. In such a configuration, virtual particles emerging from the zero-point field induce a pressure differential across the system, resulting in the environment doing work upon the plates to push them together. Although the Casimir force is commonly described as an attractive force, it is not literally a force of attraction. Rather, it is a physical manifestation of the field pressure differential acting across the system per unit area, pushing the plates together. In other words, the environment does work upon the system in search of a new equilibrium state, due to the absence of virtual particle pairs emerging from the zero-point field between the plates. An important aspect of the Casimir force equation shown here, is the manner in which it was derived. The equation shown was derived based upon a number of important assumptions, one being infinite projected plate area stemming from infinite length and breadth, another being that the temperature of the plates is 0 Kelvin. The reason these assumptions are important comes from their impact upon the physical problem they are describing. In our view, the only conceivable physical interpretation of these key assumptions would be a set of plates running parallel through the center of the observable universe, from one end to the other, somehow missing all the matter such that no matter exists within the cavity. For such an analogy, the Casimir force as derived, can only be representative of an average cosmological quantity. Consequently, our expectation is that the Casimir force should deviate from the cosmological average when a parallel plate experiment is conducted in a curved space-time manifold, for example, at the surface of a planetary body. Given that the Casimir force is dependent upon the constitution of the zero-point field, we will discuss the zero-point field in greater detail. Possibly the best way to describe the zero-point field is to describe the processes that are attributed to its constitution. In this slide we can see that virtual particle pairs spontaneously emerge from the space-time vacuum, momentarily popping into existence before either annihilating each other, or spontaneously disappearing back into the zero-point field of their own accord. We can also describe each of these virtual particles as a wave function, depicted as a family of random wave functions, as shown. The spectrum of possible zero-point field frequencies is given by the equation stated. However, a significant and substantial problem exists, that is, there is no upper limit to the frequency spectrum. This means that as the wave function frequency of a virtual particle approaches infinity, the energy contained in the dimensions of its wavelength also approaches infinity. This literally means that a vanishing volume of space-time may potentially contain an infinite amount of energy. This might also mean that, should a virtual particle pair of sufficient frequency emerge from the zero-point field into normal space-time and stay there, the universe could collapse in on itself because that point of space-time would be energetically equivalent to an infinite number of supermassive black holes. So clearly, a problem exists with the model. To stop the wheels of logic grinding to a halt, the customary approach is to spray some WD-40 on the problem in the form of renormalization in order to run the machine smoothly and ensure that the mechanism is lubricated. However, the issue with that approach is that the renormalization process is nothing more than a trick to overcome an infinity problem. In other words, Renormalization is a non-physical correction sprayed over a physical process. Hence, this is an unacceptable solution to a physically problematic model. The solution to the dilemma is embedded in understanding how matter affects the zero-point field, in terms of vacuum polarization. So, the obvious question now is, what is the polarizable vacuum? To fix the infinite energy and the vanishing volume problem properly, we need to understand the effect of the presence of matter upon the zero-point field. As this representation depicts, the presence of matter polarizes the zero-point field, such that the zero-point field may be described as a polarizable vacuum, that is, the zero-point field plus matter equals a polarized zero-point field, and the polarizable zero-point field is the polarizable vacuum. If the polarizable vacuum involves a material overlay upon the zero-point field, from this illustration, the obvious question becomes, what is the polarizable vacuum model of gravity? The polarizable vacuum model of gravity is an optical analog to general relativity. It describes gravity as a phenomenon arising from a change in energy density in the gravitational acceleration field surrounding an object, acting like a lens. No invisible grid lines or fabric, just the effects of light passing through a lens. For example, in the case of gravitational microlensing, incoming light from a source star is bent around an intermediary object by the change in the refractive index of the space-time surrounding it. This yields an identical observation to general relativity, but without the need for the unverifiable claim of space-time curvature. Within the polarizable vacuum model of gravity, the how and why mechanism for light bending around an object is clearly explicable, as opposed to the physically questionable concept of space-time curvature under general relativity. This is not to say that general relativity is wrong. The message here is that in our view, general relativity is an inferior construct to the polarizable vacuum model of gravity. However, general relativity is a mature and well-accepted doctrine, but so was a flat Earth, once upon a time too. Notably, Schwarzschild and Reissner-Nordstrom solutions exist for the polarizable vacuum model of gravity. Hence, it can be conservatively stated that the polarizable vacuum model of gravity is isomorphic to general relativity in the weak field. Thus far, we have talked about the zero-point field, its relationship to a polarizable vacuum, and how the two concepts relate to gravitational acceleration. To tie these together with electromagnetism, we shall introduce the concept of electrogravimagnetics. So, what is electrogravimagnetics? Electrogravimagnetics is a natural progression from the polarizable vacuum model of gravity, pertaining to the equilibrium between matter and the space-time surrounding it. It functions as a methodology bridging the electromagnetic and gravitational gap. It executes these three functions by describing the polarizable vacuum at any point in a gravitational acceleration field, as the summation of a Fourier series comprised of electromagnetic wave functions, and equating the summation to the expected spectral energy density distribution of the zero-point field. Once this is done, we obtain the equilibrium conditions associated with the zero-point field and the material object under consideration, for example, the zero-point field equilibrium radius of fundamental particles. The equation shown demonstrates the energetic equality between the mass energy density per unit volume of an object, and the spectral energy density distribution of the zero-point field when integrated over the frequency domain. The frequency distribution stated here is the distribution derived by Hayes, Rueda and Puthoff in their quantum vacuum inertia hypothesis, which explains the origins of inertia. However, even this distribution faces the same problem of infinite energy and a vanishing volume, as we mentioned earlier. So, how can we overcome this problem? That is, in terms of zero-point field spectral limits, what is the zero-point field frequency distribution? The zero-point field spectral limits may be computed by solving for them via the electrogravimagnetic methodology, where the polarizable vacuum is mathematically described as cubic in form, but specifically obeys a Fourier series distribution. By doing so, we are able to demonstrate that zero-point field spectral limits vary depending upon the physical situation under consideration, as depicted in this illustration. Most significantly in this diagrammatic representation, the lower limit of the zero-point field is 0 Hz, whilst the upper spectral limit is bounded by the Planck frequency. Consequently, the zero-point field is prevented from ever accommodating a virtual particle of infinite frequency. Therefore, we insist that the infinite energy in the vanishing volume problem is solved under the electrogravity-magnetic construct, because a vanishing volume can never contain any more energy than the mass energy of the local gravitational point source. So, how do we mathematically demonstrate that the zero-point field cannot contain infinite energy in flat spacetime? Let's look at an example of what happens to the spectral limits of the gravitational acceleration field, in terms of quantum mechanics and zero-point field theory, in the case of a solitary neutrally charged, non-rotating point mass at rest, occupying an otherwise empty and flat universe. As the distance from the point mass increases, the value of the refractive index approaches unity. Thus, the lower spectral limit approaches zero as the radial displacement approaches infinity. Consequently, the upper spectral limit approaches the lower limit and the spectral bandwidth converges to zero. Therefore, the spectral energy density of flat spacetime approaches zero, and the cosmological problem of infinite energy is avoided. Hence, a vanishing volume at infinite radial displacement contains no zero-point field energy. So, what can we say about zero-point field frequency bandwidths? Thus far, we have demonstrated that the spectral limits of the zero-point field depend upon the radial displacement from a gravitational point source. Moreover, we have shown that the zero-point field cannot contain infinite energy within a vanishing volume, or in flat spacetime geometry. From the previous slide stating the expressions for the minimum and maximum zero-point field spectral limits, we are able to represent these graphically, emphasizing that the zero-point field cannot accommodate a wave function of infinite frequency. All the locations depicted in this illustration exhibit finite spectral characteristics, such that the zero-point field simply does not exist at that point in space, either side of the limits indicated. In most cases, the zero-point field bandwidth extends from the millihertz to yottahertz range, and for either side of those limits, the zero-point field does not exist. This does not mean that it is a field of zero values, it literally means that it does not exist. Therefore, Heisenberg's uncertainty principle is not applicable outside those extremities. The vertical axis represents the available zero-point field pressure to act on the parallel plates. This is a very easy quantity to approximate and is computed from the change in mass energy density across the plate cavity. You can also see that a decrease in Casimir force is predicted with a decrease in polarizable vacuum field pressure. Note that I did not say zero-point field pressure, I used the terminology of polarizable vacuum field pressure. I have done this quite deliberately because the zero-point field in the presence of matter is no longer in its ground state, it has been polarized and consequently termed a polarizable vacuum field. You'll see more about changes in the Casimir force, that is, the extraterrestrial Casimir effect, in the coming slides. In this illustration, we see that the Casimir force decreases with radial distance from the Earth. The harmonic mode cutoff equation calculates the highest harmonic mode describing the polarized quantum vacuum, at position r, induced by gravitational mass m. Although the harmonic mode population increases with radial distance, the Casimir force decreases. This means that future nanoscale technology may be subject to degraded performance, or possible system failure, if design limitation countermeasures are not deployed. Similarly, the same situation applies to intergalactic spacecraft as well. The farther into deep intergalactic space a machine travels, the less effectively its Casimir force-dependent systems will work. Let's now take a deeper look at the situation a little closer to home. Application of the electrogravity-magnetic photon radiation method to the Casimir effect suggests that the terrestrially experimentally verified, neutrally charged parallel plate configuration force may differ within extraterrestrial gravitational environments from the gravitationally independent formulation presented by Casimir. Consequently, the derivation presented herein implies that a gravitationally dependent Casimir effect may become an important design factor in nanotechnology for extraterrestrial applications. However, we emphasize that we have ignored finite conductivity and temperature effects, and we have evaded the requirement for Casimir force corrections due to surface roughness. Let's now take a look at the solution algorithm generating these results. The solution algorithm may be broken into three main sections, that is, the base equations, the asymptotic correction factors, and the computational engine. It is important to recognize that the Casimir effect has only ever been confirmed at the surface of the Earth, that is, in curved spacetime. However, the original mathematical derivation of the Casimir effect involved flat spacetime, it never considered curved spacetime. Hence, the asymptotic correction factors are particularly important because they denote a recalibration of the parallel plate experiment, based upon ambient gravitational environmental conditions, at different planetary surfaces and terrestrial altitudes. That is, they consider the effects of curved space-time, unlike the historical mathematical derivation of the Casimir effect. Let's now review the computational output once again. The information contained in this frame was already tabled on slide 16. However, on this slide, we present the output as it appears in the MathCAD 8 professional computational environment. Thus, we will take this opportunity to stress that in this episode, we have emphasized the proportional change in Casimir force as a function of ambient gravitational environment, relative to the surface of the Earth. We have not accentuated its value as a force. Let's now summarize what we have learned. In this episode, we have learned that the Casimir force is expected to vary with ambient gravitational environment. That is, depending upon the local degree of space-time curvature, the Casimir force will be different in many situations. In fact, as the illustration on screen shows, we expect that the value of the Casimir force to diminish as we move radially outwards from the Milky Way galactic center. This prediction is important because, as nanotechnology becomes ever increasingly real, then nanoscale devices may be subject to complete or partial failure, if engineering designs do not consider the extraterrestrial Casimir effect presented herein. For viewers wishing to consult publications relevant to this episode, you may do so by accessing the links shown.